Hi, everybody. Welcome to another season of Dots. Elias and I are very happy to start this off again now. And today we have totally intentionally aligned talks on the theme of matchings. It's going to start off with Yuri Faenza from Colombia. So Yuri is an assistant professor at IOR at Columbia. His research currently focuses on discrete optimization in OR and their interactions with other areas, such as computational economics and school choice and market design are some of the applications that he's worked with. His projects have been funded by the NSF, including an NSF CAREER Award, at the ONR and the Swiss NSF. And we're very happy to have him. Yuri, it's all yours.
Thank you, Alex.
Oh, sorry. Let me just remind everybody of the rules of conduct. There are going to be two 25-minute talks, and then there are going to be time for questions right after the talks, but also at 2 p.m. or an hour from now, depending on where you are, there's going to be breakout rooms where you can ask the speakers questions individually. So please stick around for that if your question wasn't answered. Please put your questions in the chat during the talks, and we will field them for the speakers. Thanks, everybody.
Thanks, Alex. Thanks, Elias, as well, for organizing this very nice way of keeping the community engaged and then together. I'm very happy to give the talk today. So I'm going to tell you about some joint work with my former PhD student, Xuan Zhang, who very recently graduated from Columbia, and she just moved to Facebook research. And I'm going to tell you about matchings, in particular about stable matchings. So let's start off with the classical application of stable matchings, which you may have seen. It's school choice. So let's take a big city like New York City. Every year, roughly 80,000 students apply to the 800 public high school programs. And the phenomenon you see is what you would expect in this case is, so there would be a small set of schools that get most applications. Those are the schools everybody wants to go to. And the symmetrical is also happening. There will be a small set of students that are the star of the market. Everybody want to enroll in their schools. And well, of course, nobody will be able to go to their favorite school. So what should be a fair way, an efficient way to match students and schools to each other? And here I'm reporting a few pictures just to mention that this is a kind of topic that is interest inside academia and also outside academia. So it's a very important political issue, at least in New York City. So let me mention here that we're talking about public high schools, which means that money do not play a role. Right? So we cannot just play with costs to reduce the demand. So the most used model in this framework is the one introduced by Gale and Shapley in the 60s. And it goes as follows. So from one hand, students will rank schools in a strict manner, meaning that, for instance, Bob will rank LaGuardia first, Midwood second, and then maybe he was not ranking at all Staten Island Technical School because he doesn't want to go all the way down to Staten Island, it's too far. So we allow students to rank a subset of the schools. Schools will do the same, will strictly rank a subset of the students, and they will also have a quota, which is the number of students they can admit. Now, the schools ranking are a little bit more neat than the student ranking. They're based on many criteria. Sometimes we have ties between students. Now, we'll not talk about this. We'll only assume that those ties are broken somehow, and we're going to have a strict ranking also from the school side. That's the basic model. Okay, so an instance will look like this. Here on the left, we have the students numbered 1 to 4, and on the right, we have schools, A to D. And now this means that student 1 prefers school A to school B to school C to school D, and similarly for schools. Now, if we assume the quota is 1 in this example, then a feasible solution is just going to look like a matching. So we're going to assign certain students to certain schools. Okay, so which feature do we want our matching to have? Well, Gale Shapley introduced this concept of stability that goes as follows. So take a matching, and now take any pair that is not in the matching. For instance, you can take 3C. Now, if you look at this pair where 3 would like to be matched to C rather than with his current partner A, right? Because 3 likes C more than A. But C wouldn't want to be matched to 3 because he likes 4 more than 3. So if we want a matching to be, matching would be stable if for every pair, either at least one of the two would not want to switch and would prefer to stay with the current partner they have. And each time that there is a pair where both want to switch, we'll call this a blocking pair. So with this notation, 3C is not a blocking pair for this matching, while if you check, 3B is a blocking pair because 3 prefers B to a partner A, and B prefers 3 to 1. So this matching is not going to be stable. Cayley-Shapley showed that, well, every instance of what is called the marriage model has a stable matching, and not only that, you can find it in times linear in the size of the input, which is a great result, both on term of existence and also on term of algorithmic applications, right? Because you can find it pretty fast. Okay, so those two sides motivated the huge success of Cayley-Shapley model. I have 2 slides on this. The first, I want to talk about the practical success. So since 2003, students are assigned to public high schools in New York City, essentially following the Cayley-Shapley algorithm. I have a little asterisk there to remember. It's not exactly the way it's done, but it's close enough to that. There is some real world constraint that come into play, but it's essentially that. And this was a huge success with respect to the previous method. So it dropped down the number of students that didn't get a seat in any of the schools they wanted from 30,000 to 3,000. And if you run this in practice, so we have a few simulations, and it terminates around 3 minutes on size of the instance, on instances of the size of the New York City public school system, which is pretty good since you have to do this essentially once a year. And this has propelled the application of Cayley-Shapley in many other cities and in many other markets. Now, from a more theoretical point of view, both the concept of stable matching and the algorithm of Cayley-Shapley enjoy very nice properties. So let me mention just a couple. The Cayley-Shapley algorithm is strategy proof for students, meaning the students have no incentive to misrepresent their preference list. So it is in their best interest always to say the truth and to say really the schools that they want in this order, which of course it's a great plus for the system. Now, if instead we look at the family of stable matchings, not only we can find one stable matching using the Cayley-Shapley algorithm, but actually we can solve the maximum weight stable matching problem. This means that you look at every possible pair, student and schools, and you give a weight. And now the weight of a matching is going to be the sum of the weight of the pairs that compose the matching. And now among all the set of stable matching, which can be exponential, you can find the one that maximizes the weight. And you can actually do this both with combinatorial algorithm and with algorithms that use LP, linear programming. Now, why would you want to do this? Well, there are many things you can model with weight. You can model profit and cost to start with. You can model a function where somehow you try to find a stable matching, which is pretty good for everyone, instead of maybe being very good for one side or for the other side. You can try to force some pair to be in the matching or not to be in the matching if you really want this student to go to this school, say. And there are many things you can do with these weights. Okay, so this has been a huge success, but in the last year, people have started thinking, is stability the right concept for all the markets we face, right? And for instance, even in the school choice model, you may actually try to skew the matching a little bit more towards the students rather than the school. Stability is a very symmetric concept, right? And then there is some empirical work that show that if you do that, you can actually improve the quality of the matching for the students by quite a lot. Another thing you want to do is instead than enforcing stability that may drive actually the size of your matching quite down, you may want to match more agents, so kind of relax a little bit the stability condition to increase the cardinality of your matching, because those are seats that are that the state pays for and the city pays for. So you would want as many of them to be filled. Then there are other kind of concerns. So there is an article from a few years back on the New York Times that said, well, if you think about the strict ranking, let's say, you know, I'm ranking student by, let's say, the result is some standardized test. Then, well, you get the best student according to this criterion, but there are other objectives that you miss, like, for instance, having diversity in your cohort, right? So that's why people have been proposing many other concepts. And here I have like a very partial list, both in terms of concept and in terms of citations. So some people say, okay, let's change the output of the model. Instead of asking for a stable matching, let's ask for a Pareto optimal, a popular, a legal. Those are all concepts you can define. And some other people say, well, let's actually change the input of the model. Maybe we can assume that agents have ties in their preference list. So for instance, I told you at the very beginning, the school may have ties among students because they have, say, the same score or the same priority. How does this change the problem? Or maybe you can say, well, I don't want my preferences to be described by discrete ordering because it's not so realistic. So let's have choice functions, which is a more complex way of describing this order. Some other people change both the input and the output. This is true when, for instance, you do add a lot of complex constraints on top of your classical matching problem. And then there you can even prove that actually stable matching may not be possible at all, or maybe even if it's possible, it loses a lot of the nice property that they had, so it's not desirable anymore. So of this partial list of what have been done in the literature, what I want to tell you a little bit about today is the work we did on choice functions. So we're gonna do the following in this talk. So we're gonna, first of all, present this model with choice function, and I'll try to convince you that it's a sound model and it's an interesting one. And then I'm gonna study its structure, its algorithm, this polyhedra. And polyhedra meaning the convex hull of the feasible solution to the problem. And now, usually when you sit down and study polyhedra, what you do is start thinking of possible valid inequalities, right? And you write the right inequality, and then you say, well, does this describe the integer hull? Well, no, they have another inequality, and so on and so forth. Now, it turns out that from our approach, you don't need to do that, and the polyhedra easily follows from the first one. So we have a black box sort of tool. Once you have a certain understanding of the structure and of the algorithms for this model, then you get the polyhedra in a black box. And what I think is the interesting thing is that this is actually more general than just for stable matching. We're going to talk about problems whose feasible set can be arranged in a lattice. And now for any problem of that kind, you can apply this black box tool and obtain the related polyhedra. So we don't have other example, but we think this may actually be useful for problems beyond stable matchings. Okay, so let's get into the model. And to do that, let's do an example. So let's say you want to have choose your starting five for your basketball team. And I want to decide whether, if I like this player, this tall player here, more than this small and fast player. Now, let's say those are the 6 players I can choose from, and I have to choose 5. And you see that here I have already four players that are not so tall, but very fast. So probably to complete my team, I would want a tall player, right? Because I'm already quite good on this side, and this is basketball in the end. So I will need a tall player. So in this situation, I would like this tall player more than the small player. Now, how about here? Well, here I already have 4 tall players, which means that probably I would want some small fast player to complete my team rather than my tall player here. So in this situation, I would rather like this player than this. And you see that if you have a strict ranking to start with, you don't have this phenomenon, right? Because the strict ranking is telling you from the very beginning, do you like this player more than this, or do you like this more than that? So the way people model this is using what's called a choice function. A choice function is just a set. It's just a function that does the following. You tell me which are the candidate players for my team, and I'll tell you which are in this case, the 5 that I want. And you see that now you can have a more granular description of your preferences. And now if you're given the 6 players to form your team, you can say, I pick the first 5. And if you're given instead the 6 players, you can say, well, I pick the first 4, and then this other player, right? So it's a way more, let's say, fine-grained description of the preference. Now, if I don't tell you anything else about choice function, this can be very crazy. So people usually impose a number of conditions here. You don't have to read the formula. I'll parse this for you. So the 2 standard conditions are those 2, substitutability and consistency. So they mean the following. Substitutability is telling you this. Let's suppose that one player is chosen from a set S. Now I take a subset of S, where my player is still in. Now it's still chosen from this smaller set. Okay, so if you're chosen from a larger set, then you will be also chosen from a smaller set. Consistency means the following. Let's say that I have my set S, I apply my choice function, and I will have some set choice of S. Okay, this is the set I choose. Now, let me throw away some of the players that I did not choose. Now I do expect my choice function to give me the same output, because what I'm excluding is something I did not choose. So if you've never seen substitutability of consistency, there are two ideas that usually come up to people's mind, including mine. First is, okay, isn't this actually the same? And the second is, oh, this seems very reasonable. I cannot see a market where this is not happening. So I will leave the former for you. It's a small exercise to show that it's not the same. You can have choice functions that satisfy one but not the other. As for the second one, there are actually many situations where your function will not be substitutable and consistent. For instance, let's say that you want to choose which classes you want to take during your undergrad. And let's say you want to do algebra 1 and algebra 2. Now I'm telling you, I'm removing algebra 2 from this. I'm removing algebra 1 from the set of feasible classes. Are you still choosing algebra 2? Well, if your function was substitutable, you would, right? Because we say, if I'm choosing something from a larger set, I'm also choosing from a smaller set. But probably you're not doing that, because if you cannot take algebra 1, it doesn't make any sense to take the advanced class. So your choice function will not be substitutable. Other example is, for instance, you want two players that really play well together. So either you want both or you want none. So there are many examples where this do not apply, but in the literature, those are pretty standard, because essentially, if you don't have them, you can show that you may not have a stable matching, which I have not defined to you, but you can think that there is some concept of stability that extends for the one-to-one case to this case. And if you don't have this property, such a matching will not even exist. So those are really pretty standard. Now the third one is called quota filling. It's a little bit more standard, but we do need it. They're essentially telling you that, okay, you can throw away some player from the very beginning. Some player you say you really don't want those to be part of your team. But then if you look at the players that are left and they are less than your quota, then you're taking all of them. Okay, so if you're doing a soccer team and there are only 11 players available and all of them will be good for you in some part of the team, then you're taking all 11 of them and they will making your team with them. Okay, and now, so usually the two sides of the market are called firms and workers in this kind of model. And as I told you, there is a concept of stability that extends the classical concept of stability. You can think like absence of blocking pair, but in a choice function way. It's not really important, the precise definition. Okay, so this model, the choice function that we studied a lot, staffing problem, you can model actually diversity in schools, so affirmative action using this, course allocation, and so on and so forth. And let me remark that finding a stable matching in this model that we call the QF model for quota filling can always be done with an algorithm proposed by Roth, which is a generalization of the algorithm by Galen-Shapley choice function. Okay, so we want to ask to this question, the same question that we've seen that are answered for the one-to-one model. Can we find a stable matching of maximum weight? So now I'm giving weights over possible pairs of firm workers, and now matching is just a collection of those pairs. And now can we find one maximum weight? And similarly, can we write an LP formulation for the convex sum of the stable matchings in this model? And here I'm reporting a bunch of results on these questions for simpler model. Usually this model, they have all strict preference lists, and sometimes they are one-to-one, sometimes one side of the market can match to more. And our result extends all of this work except the work of Roth here that does not assume quota filling. It's more general than what we do, but it's only for a one-sided optimal. So it does not allow you to maximize a weight function. Let me also mention that this paper by Irving and others, it's really something we get a lot of inspiration from in terms of ideas and techniques. And so we give a positive answer to those two questions you've seen before. You can optimize a linear function over stable matching in this model polynomial time, and you can have a description in the original space of the convex hull of stable matchings with polynomially manifold strength. So let me comment on this running time here. So remember that we're describing preference lists through choice functions. Now, if we were to give the full choice function, This means that for every set S of agents from the other side, we would need to tell you which one you're choosing. So this would be an exponential size, list. And then this will completely jeopardize any interesting computational complexity question. So we assume that these choice functions are given through an oracle that essentially we go there and in some time that we denote by oracle call, we'll get the answer from that. If I have time towards the end of the talk, I'll comment on whether this assumption can be relaxed. Okay, so the techniques here is you should understand the lattice of stable matchings. So what do I mean by this? So look at all your set of the stable matchings, and now I can define a partial order on the stable matching. Well, it's not me, it's Alkan who did this. So essentially, this partial order is putting a stable matching above another stable matching if all the firms prefer the one above to the one to the bottom. So if you think of this as the Hasse diagram of your set of stable matching, then this would be the stable matching that all the firms prefer, and all the firms prefer this to this, and all the firms prefer this to this, and so on and so forth. Here's the formal definition, but it doesn't really matter. So it's clear that if you have this firm prefer, this will define a poset. Now what Alkan showed is that it actually defines a poset with a lot of structure. And these structures, it's called the distributive lattice structure. It's not really important that you know what the distributive lattice is. Think of just a very well-behaved poset. Okay, so now once we know this is true, we can use a powerful result by Birkhoff that gives us what I like to think of as a shrink representation of a lattice. So here's Birkhoff result. Take any finite distributive lattice. Now I can write a poset, and here's the poset. We call the representation poset with the following property. The elements of the lattice here are in a bijection with the closed set of this poset. What is the closed set? Well, it's just a subset of the element of the poset, such that if you have an element, you have all the elements that dominate this according to the poset. So for instance, here I have 1, 2, 3, 4, 5, 6, 7 elements in my lattice. And here how many closed set do I have? Well, I have the empty set. Then I have this one, but it takes only this node here. It's going to be 2. Then the one that takes only this node here, it's going to be 3. Those 2, 4, 5, those 3, 6, and everything 7. Okay, so I have exactly as many closed set as I have elements there. And now Birkhoff's theorem tells me no matter which distributive lattice you give me, I can build you such a poset. Now, what is the cool information here is that usually, that's not always the case, but in many interesting cases, the number of elements here, it's much smaller than the number of elements there. So if I have to now to represent the poset, I would have something that has a much smaller encoding length than what I started from. Okay, so often it's not a mathematical statement, but you can think that this is, in many interesting cases, this is happening. So in a way, this is useful because if your lattice was the lattice of stable matching, there's exponentially many elements in the number of agents, then maybe we were able to reduce this to something that has polynomially many agents, many elements in the number of agents. Okay, so that's a structural result, and by itself, it's not enough for algorithmic purposes. So what we introduce is, we introduce a concept that allows us not only to represent a lattice through this representation poset a la Birkhoff, but also allows us to shift the optimization problem over the elements from the lattice to the optimization problem over the closed set of the poset. And this concept is what we call affine representability. And this is essentially telling you that, well, there is some affine function such that if you take any element of the lattice, and so this element of the lattice is going to be the image under this affine function of its corresponding closed set. So here, this is the characteristic vector of your element of the lattice. And here I'm saying, well, I'm applying this A matrix to the characteristic vector of the closed set of the poset it corresponds to, then I'm shifting this, and then I get the characteristic vector of my element of the lattice. So Birkhoff's representation theorem, it's only telling you, it's not telling you enough information on this map that goes from one to the other. What we're saying here is that, well, this map must have a lot of structure. That's, of course, a definition. It does not always apply. But what we show is that, well, each time this definition applies, so not only your poset represents as a Birkhoff poset, but also finally represented in this term, then you can solve the optimization problems over the elements, or over the elements of the lattice in time polynomial in the number, in the size of the poset. So if you think L as being your lattice as exponentially many element, now I'm able to shift this to some problem that is runs in polynomial times on the number of elements of my poset, which we said often is much smaller. So what we do to prove that our algorithmic result that you can optimize a linear function over the set of stable matchings in this model, where we use the distributive lattice property by Alkan, then we use this result here, and then we show that actually we can find the poset that finally represents our lattice of stable matchings, and this has much smaller size than the size of the lattice. Again, altogether, this gives us our algorithmic result. Okay, now to get to the polyhedral result. So once you have an understanding of this matrix A, so once you have this affine representation, you can show that the convex hull of the elements of your lattice is just the affine image of a polytope that is very well studied. This is called the ordered polytope. It's a polytope it's a class of polytope that was studied by Stanley that has a polynomial number of facets. So this affine representation allows you to describe the convex hull of your element of the lattice as essentially the projection of some well-known polytope. And now if moreover your A is full column rank, then this description is in the original space. You really get bound on the number of facets of your convex hull. So to get our LP result that the stable matching polytope can be described with a polynomial number of facets, well, we take all this knowledge we already had about the affine representability, then we use this theorem that allows us to shift the problem from, to shift the polytope from the ordered polytope to our polytope, and then we show that the matrix A has full column rank, so this is a description in the original space. Now, this allows us actually to reprove all those results about the polytope of stable matchings that were known, and yeah, so if you're interested, I'm happy to give more details. But it's it is black box, but then so this gives you a description, but then you can open this black box and see really how your inequality will look like for your original problem. That's I would say fairly easier than describe the polytope from the beginning. How much time do I have, Alex?
1 to 2 minutes. I mean, we started a little bit late, so
yeah. Okay, that will be enough. Thanks. So yeah, maybe I'll keep this and skip the next. So when you want a lot of time when we want to prove good algorithms for our discrete optimization problems, we would like to find some structure, right? Either in our function or in our feasible region, right? So we want to prove that something is, I don't know, a metroid, or we want to prove that some function is submodular. Now with lattice is a little bit different because the lattice is a structure you put on top of your feasible set. So everything can be described as a trivial lattice that is just a chain. So for instance, here I'm describing the vertices of the cube so here is the Hasse diagram you get is a chain. And then if you write the representation poset, you get another chain. And then if you do this mapping with the order polytope, you get an extended formulation for this cube that is 7-dimensional simplex. So you get a trivial result in polyhedral combinatories that every polytope can be described as the projection of a simplex that has as many vertices as the polytope you started. Right? So if you impose like a trivial lattice structure, you get a trivial result. But then if you're a little bit more cautious and you impose on this a more structured lattice structure, then you get a more interesting representation poset and you get a more interesting extended formulation. In this case, you get the cube itself, which we know is the best extended formulation for the cube. So we cannot get better than that. So I mean, the lattice structure is really in the eye of the researcher rather than in the problem. Okay, so I'll skip this model with where we have like an explicit choice function. So let me tell you that if you're interested in stable matching problems, I really think that lattices are a powerful tool for studying them. So we've seen the results from this paper, as I said, Irving, Leader, and Gusfield also use property of lattice for maximizing the weight of stable matching in the one-to-one case. And we have a couple of recent paper that use the lattice structure of matchings for some other problems. So I think that's a very powerful tool that I suggest people that are interested in this to get acquainted with. And of course, the question is, well, how can we extend it? Can we extend it to matching models where you have a lattice structure, but it's not distributive? And can you use this to attack other combinatorial optimization problem through this lattice point of view? And yeah, so I'm done. I want to just take maybe 15 seconds to advertise the MEP workshop, which is going to happen in person, we hope. DIMAX, May 2022, and we have Margarita is one of the other organizers, and we also have a special event. It's called the Anniversary. It's a special event for Dan Bistock. Well, it was for Dan Bistock's 60th birthday. Now I think it's going to be for the 62nd birthday. Yeah, and we have a website and a lot of exciting speakers. So we look forward to seeing you there. Thank you.
Thank you very much, Yuri. In the interest of time, we will keep all questions for the breakout rooms that will happen in about half an hour after Margarita's talk, but please save those questions. I have a few. And also I'm very excited about mixedinteger.org. That's a really exciting website. Definitely, I've already visited.
Very intense, very intense website, mixedinteger.org.
Kind of like discrete.com.
Yes.
So thank you very much again, Yuri, and we'll talk to you in the breakout rooms.